So we see that the necessary parts in the for stream ciphers, just the key, the initialization vector, which should change out each time. It's a fixed value. The initialization vector is a fixed value, and so if the sender is going to create a stream cipher, or is going to create a key stream from the key and the initialization vector, then the receiver has to have the key and initialization vector also the same values, so they can create the same key stream to reverse and decrypt the message. So now we'll look a little bit deeper into symmetric algorithms, some of the problems we've run into with them, and then we'll get into asymmetric. We're going to see how they actually work, and then we're going to look at specific algorithms themselves. So the symmetric keys, we've already covered that means that the sender and receiver have to have the same key. But there are also some other issues we need to understand about using purely symmetric cryptography. There's some downfalls that we'll cover, and then we'll see what the industry came up with as solutions. So one of the things is that symmetric cryptography can only provide confidentiality. It can't provide true authenticity. And why do you think that would be? It provides confidentiality where the message is actually encrypted, but it can't prove where it came from. It can't prove authenticity, and it can't prove non-repudiation. The reason that symmetric cryptography cannot provide those services is because at least two people have the same key. So let's say I wrote a message, I encrypted it with a symmetric key, and I sent it over to you, and then somebody comes along and says, "Sean, why'd you write that message?" And I'll say, well, you can't prove it was me through cryptography because that person has the same key, so maybe they did it. So with symmetric keys, it only provides confidentiality, not authenticity or non-repudiation.